you're going to do, or the old system first. On the old system, the point of attachment is going to be considered number 1. So what you do is you identify first your complex substituent, which would be that guy right there. And then you see where it is attached. The point of attachment is going to be that point right there. That is the point of attachment. And under the old system, we name that as number 1. So what we would do here, just expand it out a little bit, I would go 1. Then I have to choose which way to go. I want to go into the longest chain with the substituent there, so I would go into the double bond, and I'd go 1, 2, 3. That's the old system. And then I would name this thing. It's based on a prop because of the 3 carbons. There's a methyl at number 1. So that substituent is going to be called 1-methyl.
Is this one that doesn't count?
They both count. They're both correct.
Oh, they're both.
So 1-methyl, and then I'm going to go prop, indicating there are 3 carbons. The double bond starts at number 2, so it's going to be prop 2-ene, and then I want to show that it's a substituent, so I end it in YL. Prop 2-enyl. And so all this would go in parentheses, and you would put it in its name alphabetically and whatnot. So the old system, the point of attachment is taken as number 1, and numbering starts from there. Okay, that's one possible way to do it. Now if you go the new way, which IUPAC has said that, I don't know why they're doing this, they said for complex substituents with double or triple bonds, the new way is preferred. You're going to run into both. ChemDraw, they switched completely over to the new way. They do not do the old way, unless it's really, really simple. Some books do the new, some books do the old. You're going to have to be comfortable with both of them. Either way is okay. The new way mirrors more IUPAC rules for even the parent. Under the new system, what you do is you find the longest chain in the substituent that contains a principal functional group. So you're going to find your longest chain that actually has the double bond in it. So what we are going to do there is our longest chain with that functional group is going to be, and I'm going to draw up above it here. I don't want to clutter it up. Right there. That 4-carbon chain that I just sort of highlighted up above. Then you number it. This is really obnoxious. I hope it's not going to last long. You number it so that the attached carbon, the point of attachment, gets the lowest possible number. That is pretty key. The attached carbon gets the lowest possible number. I don't know why they did that, but they did. And so how we're going to number this thing is, let's expand it out a little bit. We'll number it 1, 2, 3, 4. Notice the double bond did not dictate the numbering. It's the point of attachment that dictates the numbering, gets the lowest number. And then the fun begins. You name it a little bit weird. If you look at how we describe it, you can see that it's alkene number eel, which you look at and go, what? So we're going to take alkene number eel, and let's actually put it into something that we can understand, into this name. So looking at the chain, 4 carbons, it's bute. That's what alk means. It's bute, prop, pent. It's the number of carbons. So we are looking here at bute, and then dash. Then the number of the alkene is next. It got number 3. So bute 3-ene, and then 2-eel, exactly. That's the new way, and it kind of mirrors putting your numbers with what they correspond to behind the name. So you've got a double bond at number 3, and the YL, which says this is a substituent, that's occurring at number 2. Okay? Either one is okay. So what I'd like to do is practice just a bit. Let's go ahead and name this thing using, let's do the old system first. So,
We need to name the parent chain.
yep, we're going to name the parent chain and everything, and we'll use the old system first.
So loud.
It is very loud. I'm having to yell. Not fun. Okay, as far as the parent, I was coming up with, I want to just kind of highlight it, see if that's going to work out okay. That right there?
Yep.
Isn't that nice? You guys, actually, this lecture is being recorded, and I'm going to put it up on D2L, and it's going to show everything I'm doing, including all my mistakes. And as a movie, it's going to be a movie. So I should warn you, you're being recorded, so don't ask dumb questions. Yeah, I'm experimenting on you. You're guinea pigs. You just don't know it.
Where's your camera?
What's that? It's going to go on D2L. But still take notes in case it doesn't work, right? Because it's like the second time I've done this. So there's the parent. Now, in terms of numbering it, we're going to, within that parent, the double bond gets the smallest number. So we're going to be doing 1, 2, 3, 4, 5, 6, 7, 8, 9, oh my gosh, 10, 11, 12. Lovely. Okay. Now let's, we'll tackle the complex substituent in just a second because it's scary. Let's do E and Z. Do I need to worry about E or Z for the one that goes 2, 3?
Yeah. Yes. No.
If I switch those methyls, is it the same thing?
Yes.
So I don't need to worry about it. So for numbers 2 to 3, we can pretty safely say that no E or Z. I don't need it because I could draw it either way, and it doesn't matter. Now, how about the one spanning 6 to 7? Do I need to worry about it there? Yeah, if I put, right now this long chain is going opposite kind of the whole rest of it. And if I put it up, it's different. It's going to be different. So I do need to worry about that. Is it going to be E or Z?
E.
We have to prioritize each one, right? So on this side, the number 6 side, does the methyl win or the big group? The big group wins, okay. And on the number 7 side, does the pentyl chain or whatever, or the H? The pentyl. So the two number 1 groups, are they opposite each other?
Yeah.
So it is a E. Z, same side, remember? So it's an E. Okay, now we're forced to do this nightmare group thing. So what we're going to do, remember, is this is the old system. So we're going to take our point of attachment, which is right there, and we're going to call it number 1. So that right there is number 1, and we will number through the double bond. So we're going to have 1, 2.
Oh, this is old one.
I have to go up because of the methyl. It's the longest carbon chain. The chlorine's always going to be a substituent. So, what is that group? What's the name of that thing going to be? It's going to be 2-chloro, blah, 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 right? So, it starts with a C, right? Its name is going to start with a C, so I'm going to alphabetize by C, which is going to come before the methyls. So it's going to be the first thing in the name. Everyone good with that? Okay. And it is at number 5. So here we go. 5 dash. Now name it. 2-chloro. What else? There's a methyl. Don't forget the methyl. 1 methyl. And then it's prop dash 1 dash ene, right? We're doing the old way. The old way, the point of attachment is number 1. Yep. So that double bond is starting at number 1. And then just a YL. Okay? All right, this is the old system. And on the old system, that point of attachment that I labeled number 1, that dictates the numbering. So that double bond's coming off of there. Now here's something. Do I need to put E or Z on that double bond?
That's what
No. Oh,
Yeah, you do.
yes.
I do, because if I switch the chloro and the methyl on the other side, it's different, right? So I'm going to have to squeeze that in. So what are we going to call it? Is it E or is it Z?
Z.
It is Z. The chlorine one on one side, and then the giant thing one on the other side, and they're on the same side. So we are going to have to squeeze in, and I will do it right up here. Boop, Z. There we go. 1Z enol.
Oh, you want us to write it like 1Z?
Yep, 1Z. Yeah.
Professor, I thought the old way was propene 1 eel.
No, the old way I don't need the 1 eel because it's all the eel's always going to be number 1.
Yeah.
The point of attachment, the old way, is number 1, so there's no need to say it's number 1.
It's assumed.
It's assumed.
But I thought, like, okay, yeah, no, you're right. I understand that part. But I thought I'd marry the alkene with the parent.
Oh, I have to put the 1 in here because the double bond could have been between 2 and 3 as well. If I didn't tell you prop 1-ene, I wouldn't know where to put that double bond because there are some choices. Okay, now the rest of this is pretty straightforward. We have dimethyls, so 2,6 dimethyl. And now big old long name will come back down here. There's no space. I ran out of room. Now, what's the parent? What's 12? Dodec. It's dodecane, but this is ene, right? So good. And it's 2,6 E, because we did the E and Z, 2,6 E. What's the end? Diene. Do you guys see why that A was put there? Dodeca. That was because of the D right there.
You don't put a dash after dimethyl, right?
There's no dash after dimethyl. That's correct. So if I had space, dodeca would have started right after dimethyl. I just ran out of space, so I had to loop around.
You could have left that E on the outside.
I could have left the E way in the front. Absolutely, I could have.
But if you have like more than
Okay, let's try it for contrast. Existing, sure, we'll do that. It's 2,6-dimethyl, a new way. So, okay, so a lot of this is going to be exactly the same. We are going to have the same parent, the same dimethyls, the same E and Z, all that. The complex substituent is what is going to be named differently. So, looking at the new way, I am going to do it as a butte, exactly. So we're going to go here and here and here, sort of highlight it right there. That whole thing, that's a pretty weak highlight, but that whole thing counts. That's going to be a butte chain. And the rule is the point of attachment gets the lowest possible numbers. So if I'm going to number within that, what I'm going to do is go 1, 2, 3, 4. My point of attachment got a 2, versus had I gone the other way, it would have had a 3. Not as good. Okay?
Point of attachment.
Lowest number. Okay, so let's name this thing now. At number 5, it was number 5, right? Okay, at number 5, we are going to have 3-chloro, butte, 2, and it was Z. Was it Z? Yeah, it was Z. Z, ene. Now I have to say where it's attached. Yeah, 2-eel. And I've got to put the 2-eel here now. I've got to put a number because I didn't necessarily start at number 1. The old way, you always start at number 1, point of attachment. This way, not so. Okay, so you have to specify. And then the rest of it is the same. Are you guys comfortable with saying same? Yeah? Same.
It was dodeca.
It was a dodeca, yeah. Everything else is the same in it.
So does that same part start at dimethyl dodeca, or does it start at dodeca?
Well, let's back up and just do it. How about that? Let's see if it's going to let me erase. It is not. You stop that. Let's go ahead and nope. Here's what we'll do. We'll cross out the same. I have to flip out, add to existing. Okay, so then it's going to go at this point 2,6 dimethyl and we loop around dodeca, and
6E.
it was 2, there's no comma there, 2, 6E, right?
Yeah.
Yes.
Diene. So the only difference in the names was how we approach naming that complex substituent. That was it.
And the 2YL, one more time?
2YL, that indicates the YL means substituent. The 2YL means that the substituent occurred at number 2 on its chain. It was bound at number 2. Way is acceptable. Okay, so now we start reactions. With every functional group we're going to do in the rest of 420 and into 421 really extensively, we start out naming a molecule or a functional group, then talk about how to name it or how to make it, and then talk about all the reactions it does. For us, as far as formation of alkenes, you guys already know the main ways to do it. When you're making an alkene, for the most part, that will be occurring through an E2 reaction. That is the main way to make alkenes. It's the one you'll probably see 85% of the time. There are some other ways, which we'll learn in 421, but they're not as common. Okay? So this particular slide is showing you the 2 examples. We have a molecule, and we're treating it with NaOH in the first example. NaOH is not a particularly large base, so this is a small base. As far as ones that could substitute for it, we have some other possibilities. KOH, obviously, just OH minus. But you could have OR minus, where R is small, like OCH3 minus, for example. Methoxide would do the trick. Ethoxide, so that would be CH2, CH3 minus. NH2 minus would do it. Any of those small, strong bases will cause the same thing. It's an E2 elimination, and it's going to give you the most stable possible product, which is the Zaitsev product. If you wanted elimination to occur to give you the less stable option, the less stable option is the less substituted option, so that's where your double bond would be forming right there instead, at the less substituted position. I need to use a big base. So this is the one we're going to use. Potassium tert butoxide is what it's called. And it is giant. It's very sterically hindered. And what it will do is it will grab the least hindered hydrogen because it is so big. And when it does that, you end up with the less substituted product or the Hoffman product. So we have options to eliminate either way in this case. Both of them require that anti-coplanar arrangement that we talked about. That's only going to be an issue when you have a cyclic compound like a cyclohexane, and we had to deal with which H was actually anti-coplanar. Okay, and then this new word, regioselective. What that means is that if you have some possible things that could form, you only see really one thing form in its major amount. So if I were to use one of the small bases, this would be my major product. We're talking like 90–95%. It would go this way. That's a regioselective reaction. I would see very, very little of the other option. If I use a really bulky base, I'm going to see 90–95% of the less substituted option. That's also regioselective. I don't get 50–50 with these things. It selects one over the other, preferentially. Okay, another way to make an alkene would be to do a dehydration on an alcohol. So this right here, this formation of alkenes, put a little note here from alcohols. The E2 reaction we just talked about, you have to have an alkyl halide there. You need a leaving group. The alcohol is a terrible leaving group. So this guy right here, that OH, it is not going to be leaving on its own. So it's a bad leaving group. As a result, I cannot use OH minus, come in, pull a hydrogen off, and kick out the OH minus. That's not going to work. I can't use a base and get this to leave. So what I have to do is a trick. It's the same trick we saw a couple times, and we're going to protonate it, exactly. So when we add H2SO4, that protonates the OH, turns it into OH2 plus, so let's put a little 2 there and a plus, and now it's a good leaving group. These reactions tend to occur with rearrangement if it's possible. So you often see rearrangement. If you see rearrangement pretty frequently, what's the intermediate going to be? It's a carbocation. Yeah, they go through carbocation. And so the water comes off. In this case, when it came off, it went through a tertiary carbocation. My carbocation was right here at the tertiary carbon. It had nowhere to go. Look at the case below, though. It's a little bit different than that. Drag it up here and work on it. When we protonate this thing, we would end up with that, right? That's terrible. And so odds are you never actually end up with that. What it would do is, as it's forming, you're having your migration take place of a hydride. So it's going to go through this, which is much better. It'll shift to secondary. Remember, it shifts right next door. It's not going to travel far down your molecule. And then, when you actually do the elimination, you get the more substituted double bond. So it is not unusual to see rearrangements occur. Okay, so what I always do, anytime I know I'm going through a carbocation, I just kind of stop for a second, look around, make sure it's going to stay put, and if it's going to move, then move it and move on. You can't always assume things will work out nicely. Okay. That's the two main ways to make it, right? Dehydration and E2. Now, as far as the reactions go, this is just a whole lot of electron mapping pictures. What I want you guys to realize, looking at the top set of pictures, is that the pi bond is electron rich. So this blob here sort of shows it. That's what we need to know. That pi bond is electron rich. And also, the pi electrons are loosely held. They're more loosely held than the sigma. What that means is if you're going to choose some electrons to go do a reaction, the pi electrons, being the more loosely held, they're going to be the ones that can go out and grab things. And that's what we see with the mechanism of alkene reactions. Almost all of them involved the pi bond going out and attacking something that's positively charged. So the pi bond, the pi electrons, they are the nucleophile. So they're going to function as a nucleophile, go out and grab something. Then that thing, whatever it is, gets attached, and it leaves, you have attachment at one carbon, and it's a little hard to see this, it leaves a carbocation on the other one. Because electrons got ripped away from this second carbon, and nothing was put there to replace them, so it just has a positive charge. And then we'll see other things happen. So we're going to first do attack, get this carbocation intermediate, and then finish up the reaction. Sort of a general theme. Yeah.
So on the bottom, you're saying that the electrons in
The pi bond, the double bond part.
is what's attacking
Mm-hmm.
whatever.
The electrophile, whatever it is.
How will you know where the carbocation
Oh, we'll discuss that. In this case, it doesn't matter because both sides are the same. But in a lot of reactions, if the sides aren't the same, there is a preference for which side the group gets attached to. And we'll, as we go through each reaction, we'll take a look at that.
Like cis trans, which side?
No, like let's say I had something like that it wasn't symmetric, that it was like this. So is your E group, your electrophile, going to be there? Or is your electrophile, let's squeeze it over here, is your electrophile going to be there? And there are, well, it depends what reagent you use. There are reagents that will put it in the first one, And there are reagents that will put it at the second one. And they're different reactions. And we'll learn that. Each time we do a reaction, we'll talk about where it goes. And if you wanted it to go the other place, how you'd accomplish that. Okay, this is pretty much the same thing. Another thing that we'll be looking at, in addition to seeing where it goes, we're going to be looking, in some cases, when it's applicable, at syn or anti. Is it going to go cis or trans? And well, that for some of these, that's a concern too. And when we get to the appropriate place, we have to talk about it, we will. Here is an overview of the things that you are going to be learning. And this is just some of them. As we go through, we'll be learning how to, across that double bond, put a hydrogen and a halogen, or maybe a hydrogen and an OH. Then there's plain old halogenation. I just put 2 halogens on there. I can put a halogen and an OH. I can put an OH with the opposite arrangement, like that. And then we're going to even see some others. You guys are going to learn probably, when you break it all down, between this and alkynes, 20 reactions. I would guess, probably 20 different things. One thing that will help you a